Okay, this week we're going to combine and look at our weather, basically the mid latitudes, where we live. We're going to take a look at what shapes that weather and makes it. One of the first things you got to understand is an air mass. We've talked about them. You've actually had questions about them the other week with high pressure. Air masses are built under high pressure because the air doesn't move. So take a look at one here. Let's take a look at the one up in Canada, the continental polar. We're all used to getting cold air in. I'm not a particular fan of it, but it happens every winter. It forms over Canada. You think about it, this time of year in Canada, most of the ground's snow covered. They're not getting a lot of sunshine. The ground is kind of uniform. There's a large area there that's dry, that's cold. So that's where that continental air mass forms. Now, there are air masses that form up over Alaska, into Siberia, even up across the poles. They're also going to be over ice-covered areas, but they're even going to be colder because you look how much, almost no sunshine. And then you have the other air masses that form in the tropical Atlantic, for example. And what are they going to have? They're forming over water. They're going to be warm. They're going to be moist. So where these air masses come together is where everything gets interesting. Under them, typically high pressure, not a lot going on. It's where they come together that life gets interesting. So we've just talked about these air masses, and you think about it, a maritime tropical or a maritime polar air mass is going to most often have warmer at the ground. So if it goes over something that's cooler, it's going to stabilize and not mix as well. The opposite flips for the continental polars because the polar air mass is going to be colder than where it's coming over. So where they come together is a front. If that front's not moving, it's stationary. So it's simple enough. Stationary fronts. And one of the other things is warm air is always going to lift up over cold air. So if you fly through here at some elevation, you're actually going to pass the warm front on the polar side before you ever pass the warm front at the surface. So that's something that's fascinating because we've all talked about warm air being less dense. More moisture in it also helps to make it less dense. It's going to glide up and over the colder air. So a warm front is going to move north. Interestingly, the cold, dense air actually has to want to retreat before the warm air can come in. Warm air will not push out cold air. The cold air has to want to move first. Cold fronts, they're going to be very steep. Why are they so steep? Because they're very dense. So when they roll along, they're really going to have a lot of oomph with them, a lot of lifting of air. That's where you get your better chance for thunderstorms. And a heavier precipitation may occur. Not necessarily long-lived, but heavier. Cold fronts can come in all different directions. I personally hate backdoor cold fronts living on the East Coast because they come down on the east side of the mountains. And when they come down that way, they pull in air off the North Atlantic. And what do? They bring a lot of moisture, a lot of cold, and a lot of clouds. So another one is an occluded front. Basically, what happens is in a cyclone, the cold front overtakes another cold front. If that first cold front is colder, it's called a cold occlusion. If it's a little bit warmer than the other one, even though it's cold air, it pushes the warm air aloft. In either case, the warm air is aloft, and there will be precip. So, with all of this, there are normal low-pressure systems. I want you to get this. Almost every day in the winter, there is a low-pressure system across the U.S., several of them, and many times during the summer. They occur along a warm front and a cold front. These are extratropical lows. They're not tropical, they're extratropical. They don't form from tropical systems typically. They form where a warm and cold front are together, where there's a temperature contrast and you wind up getting divergence aloft. Two keys. You got to have the divergence aloft and you got to have a temperature contrast. As they develop, the divergence gets stronger, temperature contrast increases. until they eventually get that occluded shape. Notice how we almost look like a comma head at the very last one down there. Kind of like you think of a comma head for a tornado, but this is on a much larger thousands of mile scale. So they kind of form, the troughs to the west, divergence is over that area, left front quadrant of the jet typically, and gradually deepen. The trough kind of approaches it, and eventually the low and the trough becomes stacked, and that's when the low reaches its maximum intensity. It typically does not get any deeper than that point in time, and you get a lot of dry air mixing in, and gradually it's eventually going to begin weakening at this stage. They have things called conveyor belts. What they're really showing is air mass type motions. So if you look at the warm conveyor belt up out of the tropics here, is bringing warm, moist air in. Notice how it rides up over the warm front and to the north. You have a cold conveyor belt up to the north, coming off the North Atlantic in this case, or maybe off of parts of Canada, for example, bringing cool, a little bit moisture air up here, kind of rides back. This is what's bowing out the comma head. And then you have the dry airstream above it coming down out of Canada, and that can get wrapped in, causing the dry air at the surface as it's pulled down because that dry air is sinking behind the low. And here is just basically showing the typical weather. And one of the things I guess I want you to get out of this, it doesn't take a lot to have a very bad forecast. So if you look at Chicago over here, this low's gone up well west of it. And this is pretty far off. But on one side is snow, maybe the other part's rain or freezing rain, and eventually going over all rain as that warm front's coming up. Remember, there's a warm layer of there. Lots in the warm sector, you might get pretty warm. Maybe even have a little bit of sunshine from drying coming around it. And north of the east side of the low, maybe a pretty large area of rain or clouds, maybe very low clouds. Kind of miserable day. Lows come in all different tracks. If you're in Ohio or in West Virginia, a lot of the tracks form in the Rockies and come up to your west. There are some that form in Texas and the Gulf of Mexico and come up to your east. Guess which side has you a better chance of having a snowstorm? The ones that come up to your east are going to put you on the cold side of that low, so you're going to have a better chance of having a snowstorm. If they go up to your west, you might start out as a little bit of snow, but you're probably going to transition very quickly to rain. And here is just showing all of that with a winter storm. Again, extratropical cyclones, they're cold core. They get colder the further up you go, and the thicknesses are lower to the west of that low. So that is a major difference from tropical. Here's a non-occluded cold core. You see how they slope back to the west. Warm core cyclones are called heat lows. They do occur in the United States, especially in the summertime over the southwest U.S. They can get very intense heat out there, very dry, and that heat pushes the air apart. The air gets very thin, and that causes it to become very low pressure at the surface. However, because it's so not dense, so very thin air, the pressure actually doesn't drop very quickly. So you wind up actually flipping to an anticyclone when you go aloft in this core. Here you got the anticyclones that go with it. We also have lake breezes and sea breezes. And here's even better for you all in West Virginia, you have mountain valley breezes. And I have seen these in West Virginia. They're more prevalent in the Rockies, but you can actually get this. And if you're a firefighter that's trying to fight a wildfire, these are extremely important to understand which way, during which time of the day, that air is going to flip and start moving in the other direction, because it can make a major difference in how a fire would move up and down a mountainside. Chinook winds. These actually occur in California and are a big problem. You think about it, they're coming down the mountain. from the east. If they come down, gravity helps pull them down a little bit faster. They're drying as they come down. They're warming, compressional warming. So you wind up with very hot, dry air coming down off the mountain. There's Santa Ana that's occurred in California that causes major fires many times. And that is a classic example of a Chinook wind. Katabatic winds are cold winds. There are desert winds which pop up like dust devils sometimes, and they also can form dust storms. Sometimes you get what they call a heat burst, where you have a thunderstorm that actually dries out before it gets to the ground. The air that's sinking in that thunderstorm keeps getting compressed, warmer. I seen one of these that occurred in Oklahoma City when I was there one time, raised the temperature from 65 degrees to 90 degrees in a matter of minutes as that heat burst went by. There have been recordings of temperatures over 100. Even though there was no rain, it was an intense thunderstorm aloft. It didn't rain at the surface. So with that, let's take a look at what is going on now. Here's a low. So let's just see how this has evolved. 24 hours ago, the low was over California, Nevada area. It's not really intensifying very fast. Notice the cold front, kind of a, mountains make lows difficult to understand sometimes. I'll just put it that way. But here's 15 hours later. This low is getting much more intense up here with Canada. That one's doing pretty good. But this is, it's getting deeper, 990. And the latest, 991. And you can see the cold front has advanced. Here's your warm front kind of developing in this thing. As it comes out of the mountains and across, it'll have a better chance to develop. But now, if you want to look aloft with that, what do you see? A very strong jet coming down one side. Nice divergence in this area, pretty close to where the upper center low is. So you have this nice cold core. Notice how low the heights are back here to the northwest of that low. So it is still deepening. So everything is working just like you would think with this low. Don't really have a good picture on it. Here is really an example looking at mid-level drying, which shows dry air coming down along the coast of California and into this low, which is actually the jet pulling down stratospheric air, dry stratospheric air into it, making it deeper. Notice all the moisture feed. Remember the conveyor belt down here? Feeding back up into it. If we have a little bit of cold aloft coming into this area. So you actually have all the classic ingredients of an extratropical low. So when you do your assignment this week, please don't tell me there's no extratropical lows in the United States. There's one right there right now. And looking at the forecast for the next couple of days, guess what? There's going to be one. It keeps moving eastward. Notice how the warm front progresses. Here's Sunday. Here's Monday. Here's a nice intense low there. Lots of snow out in the west. Here's Monday. Another one. Oh, yeah, another one forming down here in the plains. Notice I'm not talking about Eta. Eta is not extratropical. And here's more of that. Another low forming down in the plains. Another one, even getting occluded up here in Canada with this. So look at the weather maps this week. You'll see these extratropical lows all over the place. And here's another one coming into Seattle, Washington area. So hope you enjoy this chapter. It really is putting a lot together and explaining how your weather occurs each and every day. Let me know if you have any questions.